PhD student at the University of St. Gallen. Thank you for having me today, and I will be presenting joint work with Michael Creel, who is a professor of economics at the Universitat Autonoma in Barcelona. Our work is entitled Constructing Efficient Simulated Moments Using Temporal Convolutional Networks. It's a bit of a mouthful, but it is pretty much what we try to do at this stage. As you will see, this is a fairly applied paper. There is a lot of formalism missing that I would like to try and implement in further papers. However, we do find some fairly intriguing results. So before I dive into what we really do, let me start by stating briefly our contribution. So the main idea is that we're going to propose a method to estimate model parameters that leverages the power of deep learning. So the idea is you should get a precise estimate based on the power of deep learning. And we're still going to allow you for statistical inference by using some well-established econometric frameworks or methods, right? So the idea is that in a simulation-based environment, we are going to use deep neural nets to construct an exactly identifying and hopefully informative set of statistics, right? And we show by empirical evidence that our method is able to achieve performance equal to or even better than maximum likelihood in small sample sizes, right? And in moderate sample sizes and in larger sample sizes, then maximum likelihood, of course, starts catching up as it is the fully efficient asymptotical estimator. All right, so then I would like to state also a brief motivation of when you might want and when you can use this method. So in general, as an economist, you will want to model some kind of complex phenomenon that you observe in the world. And to do so, you will prefer to do it with a fairly complex model to be able to account for what you observe in this phenomenon. And when setting up your complex model, you might be facing issues with traditional estimation methods, such as maximum likelihood or generalized method of moments. So for instance, it could be that there are latent variables in your model. It could be that you have high dimensional integrals. And due to this, you might either have an intractable likelihood or you might be facing computational constraints. Perhaps you want to recalibrate this model for different objects, right? So perhaps for different stocks multiple times a day. And it also might be that you do not have closed form theoretical moments, so you cannot do GMM. So in such a case, you would like to turn to simulation-based inference methods. Now, there might also be other approaches, but really the ones we care about are the ones that are important for this, for our work, are simulation-based inference methods. So this leads me nicely to the methodology. And the idea is that there are different perspectives and flavors of simulation-based inference, right? And a few that I have listed here, namely method of simulated moments, approximate Bayesian computation, indirect inference, and Bayesian limited information estimation, right? So the main idea behind all these methods is that we are going to match some statistics that we compute on the observed sample with some statistics that we compute on a simulated sample, right? So as soon as this idea of matching observed statistics to simulated statistics is present in your estimation method, then you might be able to use our proposed method. So in the paper, we go on and apply this to a SP500 ETF, and we do Bayesian limited information estimation, which allows us to get posteriors, and it's nice and all. But for the sake of time and simplicity, I will just mention a little bit method of simulated moments to refresh your knowledge about it if you have forgotten anything. But the idea is, as long as you're matching statistics, right, our method is applicable. And I just want to talk about the simple case in this topic, right? So let's quickly review the method of simulated moments, right? The idea is it's very similar to what you have in the generalized method of moments. You have an estimator that minimizes the following quadratic form, which is the same that you know from the generalized method of moments. You have a weighting matrix that you compute in a similar way than in the generalized method of moments. And now the only difference is this function m here, right, where instead of matching the statistics that you observe in the sample to some theoretical moment conditions, you match them to the average computed over your multiple simulations, right? So that's the whole trick. And we also know that as the number of simulation goes to infinity, then MSM becomes as efficient as the generalized moment. Now, the question remains, well, how do we choose this function f, right? So this f is supposed to be a function that takes in our data points and outputs a vector of statistics. And we would like to find some kind of optimal function f, right? So some kind of optimal statistics or moment conditions. And in practice, it turns out that it's not such an easy task. And what I have often seen in my fairly short academic career is that when you ask an economist how they decided about the moments for their models, they will answer that they're over-identifying. So they just have more moments than parameters. And we know that asymptotically, this is all fine, because asymptotically, I can keep on adding moments, and this will never hurt. But in finite samples, this is not true. In finite samples, I generally incur a bias and variance penalty in my estimator when I'm dealing with over-identification. So it would be nice if we were able to get some kind of exactly identifying yet informative statistic. And the theory here states, so Gallenthausen in their paper, Which Moments to Match, they find out that in essence, the optimal moment conditions would be your score function. And then you get a GMM estimator that is simply as efficient as maximum likelihood estimate. However, to get the score function, you need the likelihood, right? And we wouldn't be doing this whole circus if we had access to the likelihood. We would just compute the maximum likelihood estimate to start with. So in practice, what is generally done is that you have some kind of moment selection criteria that you're trying to minimize, or you have perhaps some kind of algorithm, like lasso-based algorithms. And as a researcher, you come up with this large set of moments, and according to this criterion or to this algorithm, depending on which method you're going with, then you're going to reduce this set of moments to kind of reduce your degree of over-identification, to reduce this bias and variance penalty that you would incur in finite samples. And our work somewhat falls into this category, but it's more related than something else, because the main difference is that we're going to propose a method where you don't have to come up with any larger set of moments to begin with. You just plug in the data in your neural net, and it gives you moment conditions that should be hopefully good. So how do we do this? Well, it turns out that it's not such a difficult task as long as you can simulate freely from your model. And now that is key. If your model takes a long time to simulate some observations, then perhaps you will not want to go for this method, because ideally you want to generate many, many data points. So the idea is that given a set of data points, right, which was generated by our data generating process under some parameter theta naught, we would like to recover a function that takes in the data and spits out a precise point estimate of theta naught, right? And since we are in a simulable setting, we can now just randomly sample from a parameter space. And for each parameter that I sample, I can generate some data. And now I'm trying to learn the inverse mapping, so the mapping from data to parameter using a deep neural net. And the idea is, because I have this simulable setting, I can create a massive data set for my deep neural net to learn accurately, right? So that's the neat thing. In the sense, we don't really fear overfitting too much, because we never need to use twice the same data points. We can keep on generating as long as our simulation is not too costly. And an interesting thing that we noticed when doing this is that you have to relearn a bit how you think about neural networks, in the sense that when you first learn and try to train your first neural networks, you will want to do regularizations. It could be L2 regularization, it could be dropout, and all this good stuff. But it turns out that every time you try to add this in this setting, you're actually doing worse. because in a sense, if the data generating process really is the true one, there is no need for me to kind of try to regularize my network. Okay, so I will briefly touch upon the neural networks. I don't want to go too much into details, but I'm happy to discuss that either bilaterally or afterwards, because I think now the particular architectures or the intricacies of those architectures is not necessarily too relevant for this type of conference. Yes.
If you go back twice, so where's the solution of the model at different values of parameter theta from which we simulate the data? Am I missing something?
What do you mean, the solution of the model?
So I don't know, optimal strategy, optimal consumption functions.
That is, so that's not important in a sense. In a sense, what is important is that I have data points that I observe from my, so I'm trying to recover some parameter given some data, right? And what I'm going to do is just train a neural net that, given this data, tries to learn the parameter. And because I generated from this parameter to start with, I know the hidden truth, right? So I can just do supervised learning with my neural net. Any other questions before I discuss the architecture? Good. So we chose to go for sequential modeling architectures because we wanted this to be, in a sense, general. We're going to be focusing more on time series problem, but we also show on one data generating process that is fully cross-sectional, that you can use sequential models on cross-sectional data, and this works. Might not be optimal, but it works. And so we chose two types of architectures. First, the long short-term memory networks. Since they have been around since before 2000, they have really largely dominated the field of sequence modeling, right? Until the arrival of transformers 6 years ago. And however, they do have some issues, if you ask me. And in particular, those issues is that they have, while they are called long short-term memory networks, they don't have such a long memory. Past 200 data points, it actually becomes hard to keep stuff in memory, and they have all those tricks about doing bidirectional LSTMs, if you have heard of those. But in the end, it becomes kind of complicated. And the big drawback is that LSTMs are sequential. So you cannot efficiently parallelize on a GPU the same way you could with other type of architectures, right? And nonetheless, we're going to use them as a baseline model, kind of as a baseline deep learning model to compare also how well the second model does. Did you have a question, Shine? How do you mean this?
So this LSTM stuff or so, I think that's only relevant if you have like a finite horizon stuff.
I'm not sure I'm getting the question, but we can discuss it later if that's okay for you. So then the second architecture we are focusing on are temporal convolutional networks. And those guys you might not have heard about much because they really appeared a bit in the shadows of transformers. And while transformers are neat, they are rather big and a bit more difficult to train, if you will. So if you're just dealing with a consumer-grade GPU, like I was at the time, then you might want to go for something a bit simpler that still does a good job. But we did try out transformers, and they were also getting good results, but it was just a bit of a pain to train on the GPU because they were so large that we had to reduce a couple of things. In any case, temporal convolutional networks, they were introduced by DeepMind under the name of WaveNet, and it was a generative architecture at the time, but you can kind of rewrite them to not have them generative in a sense, and they are based only on convolutional layer, dropout layers, and residual layers and normalization layers. So anything you would find in your typical deep learning toolkit, so you can easily construct them by hand. They don't come out of the box like LSTM do, but you can still kind of implement them on your own fairly easily with all the deep learning toolkits. And they have this nice property that they are fully parallelizable, and they also come with a flexible receptive field size. And the receptive field size, in a sense, is kind of the memory that I can take into account with my network. And it turns out that I can just keep on adding layers to add on to this receptive field, right? And the idea is that the receptive field grows exponentially in the number of parameters. So just one layer can double the receptive field depending on what dilation factor I choose, but those are details that I'm happy to discuss in person, or also there are some codes as to how to implement temporal convolutional networks in Julia on my GitHub. But in Python, you can just follow in a very similar manner. And those serve as the main model in our work. So let me now present you some results. I'm not sure this is working anymore. This is, okay. So what we're going to do here is we're going to look at three very simple data generating processes: a moving average of order 2, a logic model with 3 covariates, and a Garchuan 1 model. And for all of those models, it's nice because we have like a tractable likelihood. So we can compare the estimate of our TCN and LSTMs to the point estimate of the maximum likelihood. And we're going to do this for a sample size of 100, 200, 400, and 800. And the idea behind doubling the sample size is that if you have a root and consistent estimator like MLE, you will observe a reduction by a factor of 2 in the root mean square error. And this is, we don't have any proof for this, but it would be a nice hint if our network were to follow a similar trend in the reduction of the error. And we're going to look at the root mean square error averaged over some randomly drawn 5,000 parameters for which we then generate data, right? So then we have 5,000 data sets for each of those combinations. We fit those 5,000 data sets in our networks and into the maximum likelihood estimate. We average the RNSE and we compare the results. And our conjecture is that if the neural networks are able to do well, then they might also be able to do well when we have a more complex model where we don't have a tractable likelihood. And if you think about it, our networks do not care about having a likelihood available. However, it's also very clear to me that if we do have a likelihood available, it means that the model is simple. And if we don't, it might mean that the model is more complex. So of course, this is a conjecture and not in any case, right, something from which we can draw a solid conclusion. However, I will also try to convince you later on that those networks work on more complex data generating processes. So I will now, for each of the data generating processes, show you the following plot. So you have one subplot for each parameter that governs the data generating process. On the y-axis, you have the average root mean square error. You have in blue the maximum likelihood estimates, in gold the LSTM estimates, and in green the ones from the TCN. And on the x-axis, you have the process length, so 100, 200, 400, 800. And in between, this is just like this is just drawn. This is not estimated in any way. So what we see is that for those 5,000 random draws, at a sample size of 100 observations, the average root mean square error of our TCN was slightly smaller than the one of the MLE. Yes?
Sorry, I'm slow with this. Could you please, just for the benefit of Vivian, explain to us what is, because it looks like a simple estimation problem of 2 parameters, right? But you have some simulation step in between, right? So what's the input into, what's the estimation equation? What's the input into your function? What's the output?
So there is the simulation, the whole idea of the simulation is just to create the data set in a sense, right? So I randomly draw some parameters, and this will be my label in machine learning terms. And I generate some data for each of this parameter. And this is going to be the features in my machine learning vocabulary, right? And now I train the network on a lot of those simulated examples, right? Until it fits decently well. in a sense, right? And once this is done, now I redraw 5,000 parameters randomly, not from the sample I just used before, but from a completely new sample, right? I generate some data at the value of those 5,000 parameters. And now those 5,000 data sets, I'm going to plug in my neural nets, and I'm going to plug in my MLE, and then going to take the average of the RMSE, and this is what you're seeing here. Does this make sense?
The neural net is the parameters.
Exactly. So here, the neural net has an output in R2, right? And it is exactly theta 1 and theta 2.
And the objective function is some moment condition that you're trying to match.
The objective function, like the loss of my net.
Yes.
So it's just the difference between the true parameter, because I know the truth when training the model, right? And the one that the neural networks predict. There are some normalization tricks going on, but really just abstractly, you can think of it in this way. Does this make sense? Does this clarify?
Well, I think yes.
So basically, we're just doing, in a sense, L2 norm on the vector that is outputted and the true label that we know of. And this is how we train the network, right? So as you can see from this plot, what we find is that as the process length then starts going up, of course, MLE starts catching up and outperforming the TCN point estimates on average. And however, as I was mentioning before, we have this pattern of the root inconsistency in the MLE, and we have somewhat of a similar pattern in the estimates of the network. So this is good news, or it might be, we don't know yet, but this does look interesting. So for the second data generating process, which is a logic model with 3 covariates. So this is the one that is not a time series in a sense, but we treat it as if it was a time series, and that's the funny thing, it doesn't matter. And you just stack the data sequentially, even though the order doesn't matter, then the temporal convolutional net just doesn't learn anything about the ordering in a sense. It's still able to do inference on the parameters. So there what we see is a similar pattern as what we observed for the moving average of order 2 process, right? We are doing better with the TCN for 100 observations, and then as the sample size grows, MLE starts catching up. And once again, we have kind of a similar shape in this reduction of the error for the MLE as we have for the neural nets. And lastly, we do a Garch-1-1 process, and there it's even more blatant. Both the networks, LSTM and TCN, are quite clearly outperforming maximum likelihood estimates. For small sample sizes, there, to be completely honest, we also tried going for 1,600 and 3,200 samples, and then MLE, of course, starts catching up, what you would expect. It's just that it takes a long time to compute MLE for 5,000 ground samples of size 3,200. So it's a bit of an annoyance. All right, so now we have seen that in those 3 simple data generating processes, we're able to get good point estimates of the parameter, right? So we might be able to use those point estimates as moment conditions then in our simulated method of moments exam. Now, I'm going to show you as well a jump diffusion process, so a more complex data generating process where we don't have an easy likelihood that we can compute. So the idea is that you have this jump diffusion stochastic volatility model with those 2 differential equations, one for the logarithmic price, which is governed by an average drift, and the volatility, which is stochastic, and it also has a jump component. And you have the stochastic volatility, which is mean reverting, and of course has a volatility of its own. Yes, Rich?
So what are you doing? You're using the neural net as a solver for your simulated method of moments problem, but then the criterion function is buried inside the neural net. It's the loss function. How do you get point estimates? How do you get standard errors on those point estimates?
Because it doesn't matter how I compute the statistics to compute the numbers, right? So in essence, the trick that we're doing is we're just using to get point estimates first, right? To use those point estimates as a vector of statistics that we're going to match, right? So this gives us our moment conditions. And because we're doing point estimation of those parameters, we're getting something that is exactly identifying. And if the network fits well, it's informative as well, right? So we get, in this sense, a good moment condition. Good being non-formal, as I said, because this is mostly applied, and I am working on something more formal, but this is unfortunately not for today. And the idea is that once you have those vector statistics, computing the standard error is just the way you do the method of simulated moments with any kind of moment conditions that you choose. Right? Does this answer the question?
You basically have to do it one more time after you get the point estimates to get the variance covariance matrix.
Yes, so you have to run MSN then after the point estimate, right? In the sense now I'm just showing point estimates that are precise on average, and we're going to use those as a moment condition, but I'm not showing yet, or actually at all in this talk, how then this moment condition performs. I can tell you that it does perform well, in particular in the small sample cases, it's actually outperforming maximum likelihood estimates on average. However, this is not really statistically significant. Does this make sense? Thank you. So, as I said, we have this jump diffusion stochastic volatility model, right? And we have an equation for the logarithmic price and one for the logarithmic volatility. So, what are the parameters of interest here? Well, we have in total 8 parameters. So now we're going to have something that is a bit more high dimensional than the 3 parameters that we had in the best case for those simpler models. We have the average drift in the price, the speed of the mean reversion of volatility, the long-term mean volatility, the volatility of the volatility. We have a correlation between the 2 standard Brownian motions. We have a jump intensity and a jump magnitude, and here, be careful if you're not familiar with this terminology. Jump intensity is really what you can think of as jump frequency, how often a jump happens, and the magnitude is really like how large the jump is, because this is going to be relevant in just a few slides. And on top of the price that is obtained by solving those differential equations, we then add measurement error, which is randomly distributed with some volatility tau. And we solve this with a differential equation solver in Julia, and we solve this in continuous time, or at least as close as you might get in a sense. And what we then do is for 1,000 time steps, so 1,000 days, we're going to aggregate the log returns, realized volatility computed at 10-minute intervals, and by-power variation computed at 10 minutes intervals. Right? So at the end of the day, I have a time series that is of length 1,000 with 3 covariates or features in there, right? So far, so good. So what I'm now going to show you is the kind of similar to what I showed you before with those 3 simple data generating process. I trained the network first on a large set of data that took a long time to generate. But once the network is trained, the estimation is near instant, right? It's just matrix multiplication. We just have to do the training once on a large set of data. And once this is done, then I'm just going to draw 5,000 random parameters, generate those values that you can see here, those 5,000 parameters, and plot them into the network. And on the following plot, what you see is a subplot for each of the parameters, right, of our parameter vector. On the x-axis, you have the true value of the parameter, and on the y-axis, you have the value predicted by our network. So if our network was doing a perfect job, we would be matching the diagonal on all those subplots. And I don't want to brag, but we're close to matching the diagonal on many of those parameters, if you will. And there is one that is looking fairly strange, and this is lambda 1, the jump magnitude. So what is going on? Why are we failing so badly at estimating or at getting the point estimate of the jump magnitude? Well, remember this jump intensity guy. If we have a jump intensity that is lower than 0.01, then on average, I would not expect to see a single jump through 1,000 days, right? So I have an identification issue. If I'm not observing a jump, how am I going to learn or to tell the jump size, right? This doesn't make sense. So on the left-hand side, you have the estimates of lambda 1 when lambda 0 was smaller than 0.01. And now, be careful, this is on average. This is on average that you do not observe a jump. There might be points in there where we did observe a jump, and but most of them we did not. And then on the right-hand side, we have when lambda 0 is above 0.01, and on average, we would observe at least one jump over 1,000 time steps. And there we see that our network is doing much better. And perhaps what I should have mentioned before is you have those little dots, right? Each one of them is a single parameter draw, and then I just plotted the kernel density estimate on top because it's a bit hard to see where the dots concentrate otherwise, right? Okay, so then let me conclude, and then we'll come to any eventual questions. So we have a very interesting case with those simulation-based inference methods. In a sense, we have a best-case scenario for deep learning as long as we can generate enough samples, as long as our simulation process doesn't take hours and hours or even days. And once you have trained the initial network, you can reuse this to construct your moment conditions on any further estimation problem, right? So let's say I want to do Garch modeling for stocks, then I can just train it once on a large sample space of parameters, and then every day I could redo this for multiple thousands or even millions of stocks easily, because neural networks, once the training is done, once we're doing inference, and there it's not statistical inference. When we talk about inference, deep learning is generally just prediction. So the prediction is very fast. So we are really limited only in the cost of simulation. We find promising results on, I think this just run out of batteries, so I will try to talk a little bit more loudly. I hope you can hear me in the back. Is it fine? Good, thanks. So we get promising results on 3 simple data generating processes, and also one that is moderately complex, this jump diffusion stochastic volatility model. And it's a really easy to implement methodology, if you will. We have a full Julia package, which is still under development, to be completely honest. But it's already functional. There might be some documentation missing. You might run into errors, but please just email me. I'm happy to look at it, or open an issue on GitHub, even better. I don't mind. It's on my GitHub. I'm happy if you want to look at it. There is also the code for the temporal convolutional networks on my GitHub in Julia. I also did a version of it in PyTorch for the Bank of Italy, who has a black box calibration toolkit for heterogeneous based agent models. So if you want to look at how this works in PyTorch, you can have a look over there. But the some of the authors of this temporal convolutional networks also provide the code in PyTorch. So you might want to look in there as well, because our versions are a bit reduced. They don't use dropout or any kind of regularization. One last thing that I forgot to mention earlier, right? When we are training the network on this jump diffusion stochastic volatility model, instead of doing uniform sampling of the parameters, because we don't want the points to kind of clutter at the bounds of our hypercube, what we do is Sobol sampling. It turned out that both methods worked pretty much exactly the same. Even if you don't do Sobol sampling, the network was giving pretty similar results. And there are also some other wild things that are happening. In fact, we found that the network was, for some reason, able to extrapolate properly to parameter values it had never seen before that were outside of the bounds that we sampled. All right, that's it. Thank you for your attention, and I'm happy to take any questions that.
Yeah, we have about
Yes.
5 minutes for discussion.
So towards the end of the talk, you said that, you can ask, an economist when they do an S&M, well, how did you choose their moments? And you say, well, they respond with, well, it's over-identified, so it's all okay, which is a flippant answer for them to give, but I also don't think it's the answer that's really given. Usually, in the refereeing process, you need to explain how does your identification work? What is the mapping from, what's the story you're telling? And, you move a parameter, what happens in your model? And the moments are chosen because you say, these are the important features that move with my parameters, that's why I chose them. And then I bound my hands. I say, I'm going to try to fit these things, efficient every which way, and I'm not going to throw things out unless it goes to generate my model and I say I had to throw them up. In yours, your method, you ask the neural network, well, what's important? And you have it answer the question of what's important. And then what comes out the other side, for expression, I see how we could do, get standard errors by just, using methods once we have those moments, but how do we interpret those moments, right? Like I can describe for you, even if I had 1,000 moments, I can tell you what is there's 7 classes of moments and there's 150 of each, and I can describe them for you. How, for these moments, they could be going every which way and not be humanly describable, or at least each one would be completely different description. Like, what does it mean at the end?
At the end, you can kind of interpret it as a sufficient statistic, or as a close to being sufficient statistic, if that makes sense. And you're a statistic that is also exactly identifying, so you don't have this over-identification case, right?
Oh, does it choose number of moments equals number of parameters?
Yes.
Oh, so in a non-
Because you can, you set up the network, right? So I also set up what is the dimension of my output. And for any given problem, I will just say, okay, dimension of the output has to be the same dimension as the number of parameters, right? And then you interpret them as a sort of sufficient statistic, right? But that's also not something that we have formalized in here. As I said, this is unfortunately for the moment largely applied. Does that make sense?
Sort of, yeah.
There was another question right next to you. It was a similar thing. Oh.
There was another question.
So
Yes.
you kind of touched it at very interesting here.
Thank you.
Touched it at the end, which is, in these low-dimensional examples, you can sort of come up with an approximating model that covers the entire parameter space, and presumably it's reasonably accurate. But in real-world examples, you might have to actually sort of sample from the sample space in some sense, or you're not. We can't. So you can imagine if you had prior knowledge about what the true parameters are, you might more intensively have your model predict theta well in that.
Yeah. So.
And I don't even. That suggests maybe even an iterative process where you would.
Yeah. So.
Improve, figure out roughly where the.
So this.
Is and then.
Actually, we ran into, when estimating the example on the SPY ETF, which I did not present here, but it's in the paper. And what happened is that we had set one of our parameter values to kind of be too narrow. And it was giving us estimates outside of this value. And then what we did is simply completely throw away this network, start from scratch with a larger parameter size. So yes, that's the way one could implement prior knowledge. And of course, you don't need to go with that neural net estimation to begin with, right? You can do some kind of other estimation and then perhaps take bounds around the parameters that you would get there, and then train your neural net on those bounds.
I think we have time for one more question. Well then, please join me in thanking.